Hey everyone. So I wanted to talk a little bit about the definite integral, which there was a definition of in a previous video. I want to reemphasize some things about it and do a little example of one way in which we can use it. So let's just state it first. It's got a lot of words and information in it, but it's actually something we've been talking about in over and over again since the beginning. So if f is a function defined for a less than or equal to x, less than or equal to b, so between two values a and b, we divide that interval a and b, a to b, the closed interval a, b, into n subintervals, the width of which is going to be delta x, which we define to be b minus a over n. We let x0, x1, x2, and so on up to xn be the endpoints of the subintervals, with x0 equals a and xn equals b. And then we'll let xi star or x star I be any point in the interval xi minus 1 to xi. Then the definite integral of f from a to b is, and that symbol we just say, the way I just said it, this new symbol on the left here is the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star delta x, provided this limit exists and gives the same value for all possible choices of xi star. In this case, we say f is integrable on ab. Okay, that was a mouthful. Let's dig into what this means again. So it's just what we've been doing. I have a function, let's call it f. So here's a function f. It's defined between a and b, right? So that's the beginning. We split up this interval a to b into subintervals. The width of each one is delta x, which is equal to b minus a over n, right? Just how long is the whole interval divided by how many pieces are there. We label these as x0, x1, x2 on up to xn, right? This is just everything we've been doing, just laying it all out. And then one difference here is this definition has this x star sub I, which is any point in the interval. So for instance, if this is the interval x sub I minus 1 to x sub I, x star sub I is just any point in this interval, right, including the endpoints. I've been choosing the right endpoints, right, because it shouldn't matter which one. But the truth be told, you can pick any point in this interval for your sample point, x star sub I, okay? So then we get this symbol, but on the right-hand side is something familiar. It's just the value of the function at the sample point. So for instance, if my x star sub I in this interval is right here, the value of the function is up here, and this product, f of that sample point times delta x, is just the area of this rectangle. Okay, that's all that thing here is. The sum would be adding up all the areas if you made rectangles in each of these intervals. I'm not going to do it, it'll make the picture too messy. And then the limit says what happens if we keep making those more and more rectangles. So the intervals are getting smaller and smaller. And as we've seen, what we're doing is getting better and better approximations to the area between this curve, this graph of f, and the x-axis from a to b, right? So this shaded blue area. So that's what this limit should equal, right? Of course, we have to have the limit exist, and then we also have to have this other condition that that it doesn't matter our choice of xi stars, right? Now, this is a little bit trickier. We don't need to worry about this too much. All we're going to need to know is that our functions are continuous or at least if they are discontinuous, they have only jump discontinuities and a finite number of them. All that means is its picture could look something like this. Our function might go to here and then jump up like this, and then maybe jump again and do something like that, right? So you can have these jump discontinuities where it suddenly changes value. Here's the x-axis. We could still find this area because it's just going to look like this. This is still a shape we can find the area of. The only problems we have to worry is if we have a discontinuity that's an asymptote, right? If we had an asymptote for one of these, for instance, if instead of a jump discontinuity there, we had an asymptote and our function did something like this, going off to infinity, well, then you've got an infinite area there and that limit's not going to exist. Although we'll find out there are actually some times we can still make sense of it, but that's further down the road. We have to use other methods for that. Or if you have infinite jump discontinuities, we're not even going to approach that. That's just very, very well ill-behaved functions that are not the kind of things we're going to leave. So essentially, any piecewise function or any of the typical functions, exponentials, polynomials, root functions, those kinds of things, wherever they're defined, should work for this, except for those rational functions that have asymptotes, or natural log and things like that, things that have asymptotes. Okay, so what I really want to focus on right now is the fact that a couple things. A, we remember that this limit here, which we've been talking about in earlier videos, gives us this area that I've shaded here. And B, this new thing, this definite integral, isn't a new thing. It's just a new symbol. I mean, that is a new thing, but it's not a new idea. It's just a symbol for that thing we've been talking about. So this symbol here on the left, the integral from a to b of f of x dx, is a symbol for the number, right? This thing is a number over here that represents the area from a to b between the graph of f and the x-axis, okay? Now notice it looks like we have the variable x in here, but this doesn't depend on x, right? X is just telling us, it's just defining the function, right? But this curve is defined, we can use any variable we want. This is a number and that number doesn't change if all these conditions are met, okay? And that number represents the area as I've drawn here. Okay, so one of our jobs in this class, in these videos, is to figure out how to take this limit, okay? However, there are times when all we need to do is understand that this limit represents the area here. So let's do an example of a definite integral where we can get around taking this limit, which would be very difficult, by using the fact that it represents an area. So for instance, let's take the definite integral. I've got the integral from 2 to 5 of 7 minus 9 minus the quantity x minus 5 squared, and all of that to the 1/2 power, right? It's a pretty ugly looking thing, okay? This is our f. This is our f of x, right, from the definition here. And so this thing here is equivalent to the limit as n goes to infinity of the sum from I equals 1 to n of f x of I star delta x. We'd have to go through and name our sample points, define what xi is, what delta x is, and all that kind of stuff. We're not going to do that. Instead, we're going to remember that this represents an area. So let's look at this function. I'm going to write this function. And let's do a little bit of algebra. So I've just subtracted 9 to both sides. And now I'm going to square both sides. So on the left, I get this, Over here, the negative goes away when I square it, and I get rid of the radical, the 1/2 power, the square root here, to get 9 minus x minus 5 squared. And now I'm going to add that x minus 5 squared to the other side, and I get this. X minus 5 squared plus y minus 7 squared equals 9. Okay. Now, it was probably not obvious when we started what this thing was, but you may remember this form somewhere back in the recesses of your memory. This is the equation of a circle. This is a circle with center 5, 3 and radius, 5, 7 and radius of 3. Okay. That's what we're looking at here. Now, with that in mind, we can probably figure out the area without having to take this limit, because remember, this definite integral represents an area. Okay, so let's try to make a graph of what we're looking at here. So I'll draw a couple axes. And let's put in some hash marks maybe. So I'm going to need to go 1, 2. Let's make them a little further apart. Sorry about that. All right, here we go. 1, 2, 3, 4, 5, 6. So those are my units. 1, 2, 3, 4, 5, 6, 7. All right. So I just said this was a circle with radius, center, center 5, 7. So here's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. The center is right here. Let's put a couple of points in and then draw the circle. So for instance, since the radius is 3, if I went to the point right below it, it should be at 5, 4. Same exponent. This is a point on the bottom, at the bottom of the circle. Same center, x coordinate, 4 lower on the y coordinate. I can do the same thing going out in this direction. So I want to be out to 2. Right, I'm going 3 units to the right. There'll be 1 above. Looks like it's going to be a bit off my screen, and then there should be 1 over here. Right, so the picture is more or less like this. Now, that's the graph, that's the points that represent the solutions to this equation. This is our actual function. Right? This function doesn't represent all of these points. These points aren't even a function, right? Because it doesn't pass the vertical line test. There are more than one output for a single input. However, it's easy enough to see what this function is, what part of this picture of the circle is represented by this function. Look at our function, y equals 7 minus 9, the quantity 9 minus x minus 5 squared, quantity to the 1/2. This thing in the square root is always going to be positive. We're taking 7 minus something positive. Well, that's going to give us something 7 or less. And so this picture isn't quite accurate. The y, the function we care about, is actually only the bottom half of this circle. So pretend I drew that exactly on top of the bottom half of that circle. And so the big insight to have here is that this integral, this definite integral from 2 to 5 of our f of x dx, is the area. We're going to go from 2 to 5 below the graph of f and above the x-axis, between those two things. So this is the area we want. Okay? So we don't have to use any calculus as long as we recognize that to compute this area. First of all, notice I can make this rectangle. This rectangle is 7 units tall 3 units wide. So let's just write area of rectangle is going to be, what did I just say? 7 by 3, yeah, 7 times 3, or 21 units of area. We also know this area in here, this pink area, right? That's a quarter of a circle. So let's just call that area pink. That's going to be 1/4 pi times the radius squared. And we said the radius was 3, so the radius squared is 9. Right? But we're taking a quarter of it, so we're going to get 9/4 pi. Which means this integral from 2 to 5 of 7 minus the quantity, 9 minus 5 minus x squared to the 1/2, this horribly dx, this horribly complicated set of symbols here. Well, just look at this picture. We take the rectangle area and we subtract the pink area. We're left with the blue area, which is what represents what this symbol, these symbols are representing. And so it's just going to be 21 minus 9/4 pi. Okay. Now, the big point here, okay, a couple of things. So the big points. A, recognizing that this new symbol for the definite integral is just a new symbol for the stuff we've been talking about since the first video. How do we compute these areas? And we defined the area to be this symbol, and so, sorry, to be this limit on the right. So we gave it a symbol because it's something we want to do a lot, so we might as well have its own symbol. Okay, we don't want to write this whole limit thing all the time. That's one thing. 2 is reinforcing that this symbol represents an area, the area between the graph of the function and the x-axis. In the last video, I did mention sometimes these areas can be negative, which is not something we usually think about, but the definition geometrically, if the height of the function f of x sub I is negative, you're going to get negative areas. Intuitively, or maybe that's not the right word, but the meaning behind that, for instance, we did a previous video where we talked about how these areas can represent something like distance if you have a velocity function. Well, if you're moving backwards, your distance is going to be in a negative direction. That would be a negative area. Your velocity being negative or backwards would be negative, so it's below the x-axis. Okay? But the big point here is this connection between this symbol and the area. Just like in Calc 1, you connect the derivative to the slope of a tangent line. Now we connect this definite integral to the area between the function and the curve. Okay? And then the last point is, this f of x, we call this the integrand, the thing you're integrating over, the function you're integrating over. That thing here is complicated, right? We will eventually learn shortcuts, learn how to take these integrals without using geometry. There's a process we will go through. However, sometimes it's still easier to use geometry. This would be a difficult integral to use. You'd use some trigonometry that we'll get to talking about later. But even if we knew that, even if we already had that method under our belt, this one would always be, to my mind, is easier to do with this geometry, right? So if you recognize that this is a little piece of a circle, this becomes a pretty standard, pretty straightforward problem to do. And so while it's not wrong to do it the other way, if you spend some time using this kind of method, you can save yourself a bunch of time if you recognize something to just be a simple geometric shape or a combination of simple geometric shapes that you already know the area for. Okay, that is going to do it for this one. Thanks, everybody. I will see you next time.